Hello everyone, today I will be presenting my ECG signal filtering product using the Kalman filter in Python. As you know, ECG signals are often corrupted by noise, making their analysis challenging. In this video, I will explain how we implemented an effective solution to clean these signals while preserving their vital information. You will discover the code, the results, and the practical cases tested. Let's get started. This is an ECG recording. We can see that the lines are clear and regular. The waves like the P wave, the QRS complex, and the T wave are easy to see. There is no noise or shaking in these signals. This is probably because of a Kalman filter or a smoothing filter we used. This kind of filter helps remove unwanted signals like electrical noise or muscle movements. That way, the ECG becomes easier to read for doctors, the important parts of the signal stay clear, and the recording looks more stable. But we have to be careful. If we use too much filtering, we can change the shape of the signal. That can hide most important information. So it's important to choose the right filter to keep that signal clean, but still true to the real heart activity. This graph shows a signal from a sensor over time with and without noise. The red line is the clean signal and the blue line is the noisy signal. With 5% noise added, we can see that the noise makes the signal more irregular and harder to read. The blue line has a lot of small, fast changes that do not exist in the original one. These changes are caused by noise, which can come from electrical source or a sensor movements. This part is important because it shows how much a small amount of noise, only 5%, can affect the signal. If we want to process or analyze this signal correctly, we need to remove or reduce the noise using a filter. Without filtering, it's difficult to detect the real features of the signal, especially when we work with ECG or other biomedical signals. Here we zoom in on a small part of the previous signal. Now we can see more clearly how the noise affects the shape. The red line still shows the original one, and the blue line is the noisy one. We can see that the blue line follows the red one closely, but with small difference, small peaks and variation caused by the noise. This zoomed view is useful because it helps us understand how filtering works at a detailed level. Even if the noise is small, it can change the values enough to confuse signal analysis. This is why filters are so important. They help clean the signal, so we only keep the important information. In the next parts of the presentation, we will see how to apply filters to fix this problem. Why did we choose the Kalman filter? Unlike traditional filters like FIR or IIR, which have fixed responses, the Kalman filter adapts dynamically. It combines real-time production and correction, making it more effective processing variable signals. The Kalman filter operates in two key phases. The first one, the time update projection, predicts the next state using the state transition matrix F given as xn(n-1) and the projecting the error covariance pn(n-1) with added process noise Q. Next, the measurement update, which is estimation, refines this prediction. The Kalman gain weights the difference between actual measurements and our prediction, updating to the state and reducing uncertainty in Pn-1. This diagram illustrates a typical system using a Kalman filter. Here U represents control inputs, Y and V are process and measurements noise, and Y is the system output. The Kalman filter process noisy measurements to estimate true state X. Such Steps are common in robotics, navigation, and signal processing, where noise filtering is essential for performance. Now we zoom on the code. The core of our solution lies in this function. It follows two main steps. Prediction, like the filter estimates the next state of the signal based on the previous model, and the correction, it adjusts this estimate using new measurements accounting for their reliability. The parameters Q and R control the confidence in the model and the measurements respectively. This flexibility allows the filter to adapt to different types of noise. As we can see, this is our results of our Kalman filter. The MSE of the noisy filter was 1.37 times 10 to the power of -2, which was reduced to 8.67 times 10 to the power of -3 after filtering, demonstrating a significant improvement in accuracy. This matrix confirmed that the Kalman filter effectively reduced noise and enhanced signal quality, making it a powerful tool for applications like sensor data refinement or real-time tracking. This analysis compares ECG signals original noisy 4.62 dB S1R and filtered 6.60 dB SNR. The Kalman filter maintains QRS complex while reducing noise. The time domain plot 0 to 10 seconds shows filtered amplitudes converging towards the original. Like a result, we can say that the filters enhances signal fidelity for clinical use. This analysis evaluates Kalman filtering on 3 ECG types: normal, record 101, arithmetic, and age, record 118. Key results: the normal ECG, minimal S and R change, indicating stable signal fidelity. The arithmetic ECG SNR improved from 5.7 dB to 8.9, critical for detecting irregular rhythms. And the aged ECG dramatic SNR enhancement, enabling clearer analysis and degrade signals. So, like a result, we can say that the filter excels in pathologically and low S&R conditions, proving robust and for clinical diagnostics. In conclusion, our Kalman filter provides an effective solution for cleaning ECG signals, paving the way for reliable portable medical applications. Thanks for watching this video.